Alright, so let's talk about finding normal probabilities. A normal probability, let's write this down. This is basically the probability that you're going to find under a curve. The normal curve represents probabilities. So we associate this curve with an area of, all the area underneath here is 100%. And we can associate that with any probability or any likelihood of anything occurring. So when this starts to happen, what we're going to do is this. The first thing we're always going to do for any type of problem is shade a curve. And there are 3 types of curves we're going to learn to shade. The first curve is called a lower or a left curve. And it involves words that mean like below or less than or things like that. When you see those words under, you're going to shade a curve that looks like this. And the way it works is you draw a normal curve first. And we're always going to standardize our curves. We're going to let our mean be 0. And on this curve, you're going to locate whatever the z value is that you find. So your z may fall right here. Whatever the z value is, a left curve means you're shading it to the left. So you're finding the area in the curve that is to the left like this, or the lower area of the curve. When you have a problem like this, your probabilities will look like this. The probability that z is less than or equal to whatever this z-score is right here. We also find things for what we call an upper curve, or this is a right curve, and those involve words like above, more than, at least. Those are going to be your upper curves. An upper curve, and you always draw a curve for these type of problems. Locate your mean at 0. Your upper curve, your z may still sit here. But when you're finding an upper curve, you're finding everything to the right of that curve. So you're finding the right tail area. When you find right tail area, it looks like this. The probability that z is less than or equal to whatever this z-score is again. That's what the big Z represents right now. And you're going to find that area using your calculator. The third type of curve is what we call a between. And in a between, you have 2 z values that you're going to find. So your means here is 0. You have z1 and z2. And the area you're calculating now is in between those 2 values. So when you calculate this to write this probability statement, you're going to say the probability that the z value is in between z1 and z2. So whatever that's going to be now. Now, to find these, what ends up happening, you're finding areas, so you need to be able to integrate. Because most of you haven't taken a calc class to learn how to integrate. We're going to integrate using the calculators. In the calculator, this says each z-score corresponds to a particular area under the normal curve. The areas are probabilities, remember that. And we're going to use your calculator. And in your calculator, you have a function called Normal Cdf. To get to Normal Cdf, you press the second key, and you're going to press this bars key, which brings up your distribution. You're always going to use Normal Cdf. Do not use the PDF. PDF stands for probability density function. CDF stands for cumulative density function. The normal curve is a cumulative function, so you always use number 2. Always use the CDF. So the CDF syntax, when you write it in, so again, to get there, you go second, you go bars, you go normal CDF. Alright, so again, second vars normal CDF. And the syntax for normal CDF. So the way you're going to have to write this function is like this. When you plug it into your calculator, you're going to see different things in your screens than maybe mine. You might have newer software. But the general syntax, when you click on that, normal CDF wants you to give it 4 things. It wants you to tell, basically it wants the, what we call the lower bound first. Then it also wants the upper bound, whatever that may be. And then you can also specify with a mu and a standard deviation. And remember, the mu and the standard deviation are these are the parameters of a normal distribution. So you'll have to know those. If you're finding a z-score though, and your calculator always does this, it defaults automatically to 0 and 1. So if you're finding z-scores, you don't have to type anything for those. But if you're not finding z-scores, you're going to have to type in values for those. We'll do it both ways in a second. And what that means is this lower and upper bound just means this. When you draw these curves, in order to integrate, you actually need fixed points. On this curve right here, these curves are asymptotic along this horizontal line. They're never going to touch that line. So really and truthfully, you can't bound the actual area. But as you get closer and closer to the line, or if the number gets really, really small, or really, really big, well, when it gets really, really small, it goes to negative infinity. Your calculator doesn't have a negative infinity button. So what it does is it approximates negative infinity by using some really small number. We generally say when it's anything that's really small to the left, we call it this number here. Just a whole bunch of 9s. I normally put 4 or 5. You can put however many you want to, though. You just want a really small number. For a really big number, when it comes way out here, it's the same setup, so a bunch of 9s. So put as many 9s as you want to. You just want a really big number out there. We're going to do this example starting with this problem over here. It's talking about the weights of steers or Angus steers. And in this problem, we're going to look at how to actually input this into the calculator and how to calculate the area for it, all right? So this says, using a normal model with a mean of 1,152 and a standard deviation of 84, the weights of Angus steers, what percent of steers weigh? So this right here tells me that I'm going to start calculating actual areas. The word percent or proportions are, when you see probabilities, that means you're calculating the area underneath the normal curve. So we know that our normal model is defined like this. X is approximately normal with a mean of 1152, standard deviation of 84. This says I want to calculate over 1250. When you start any one of these problems, you're always going to draw a curve. So I'm going to draw a curve for this, a normal curve. And on this normal curve, I'm going to set the mean, which is at 1250. I'm sorry, which is at 1152. 1152. So set the mean of the curve 1152. Locate this value 1250 on the normal curve. Is it to the right or to the left of 1152? And this one falls to the right at 1250. The key word here is the word over. So when I'm looking at over, I'm going to draw this line. Over means greater than or to the right of that curve. So this is a upper curve or a right curve. So the way this works now is this. The first thing you're going to do when you have one of these problems is find a z-score. So find a z-score for this. So remember, z is equal to the x value, which is 1250, minus the standard, the mean, which is 1152, divided by the standard deviation, which is 84. So that's 1250 minus 1152. 84. I get a z-score of 1.167. That means if this curve were a standardized curve, this value would be 0. Your mean would be 0 of that curve. And this value out here would be equivalent to 1.167. So when we find this area, here's how you report the actual area now. So I'm going to report the area for this curve on a standard normal. So to report that area, I'm going to do the probability that, well, since it's a right curve, I'm using this symbol right here. This is actually wrong. This needs to be changed to this. It's greater than or equal to. So I'm going to report greater than or equal to. So I want the probability that z is greater than or equal to this z-score right here, or this z-score right here, which is 1.167. And now I use my calculator to find this. Here's how you find this in your calculator. You're going to use the command Normal Cdf. And when you look at this, you drew this curve to look at the actual picture to help you do this. Your lower bound of what you're trying to calculate is this number right here, or this z-score, which is 1.167. The upper bound is some number way out here. Remember, we said that number way out here, going this way, is just a whole bunch of 9s. So we're going to use our calculator to calculate this number here. And you do second vars, normal CDF. The lower bound is the z-score, 1.167, comma, a whole bunch of 9s. And you do this. And this tells me that the percent of steers who have weights over 1250 is equal to about 12.2%. There's about 12.2% of steers who have weights over 1250. The quicker way to do this, and we're going to see this way in a few. Once you learn how to do z-scores and are able to actually understand what a z-score is doing, I won't mind you doing this, but as of right now, I want you to find z-scores. But the quicker way to do this is actually to do normal CDF. And instead of converting to z-scores, use the numbers that were given to you. Well, we see that the lower bound here is 1250. The upper bound is still some really big number. And this time what you can do is input the actual mean and standard deviation. Up here when we didn't input the mean and standard deviation, it was understood to be 0 and 1. When you actually input the mean and standard deviation, we're going to get this time. 1152 and 84. So let's plug that one in and see what we get. Second vars, normal CDF. This time using the actual values that were given to it, we'll plug in 1250, which is the lower bound. The upper bound is a bunch of 9s. The mean for this is 1152. The standard deviation is 84. You press enter. You see how you get the exact same number as the z-score? So, the next one, under 1,200 pounds. Again, the first thing you're going to do is draw your curve. So this time, you set your mean again at 1152. Find 1,200, which is out here somewhere. You want to know under 1,200. Means back this way. Under 1,200 means to the left. This is the left curve. So find your z-score again. Z is equal to 1,200 minus 1152 divided by 84. So 1,200 minus 1152. Calculate that. I get 0.571. So that means this value, if this were a z-curve, would be 0.571 is the actual z value. And look here, when you calculate this, since it's a left curve, you're going to do the probability that z is less than that z-score. So in your calculator, you're going to do second vars, normal CDF. The lower bound for this curve now, if you look out here, is just some really, really small number. So negative 9s. Up to the upper bound, which is, if you look here, is this z-score now, which is 0.571. When I get that, I get this z 0.716. So about 71.6% of steers have weights that are under 1,200 pounds. And again, you can do this the short way by doing second vars, normal CDF. The lower bound again is these negative 9s out here. The upper bound is this number right here, that 1,200 this time, instead of changing to a z-score. Leave it at 1,200. The mean is 1152 of the distribution. The standard deviation is 84. When you do that, you get the exact same thing. A little round off arrow on that, because we rounded off our z-score. The next one says between 1,000 and 1,100. So again, first thing you always are going to do is draw a curve. On that curve, set your mean at 1152. This time, 1,000 falls back here, and 1,100 right here. So I want to go in between these two values this time. This is one of the few times where it's going to be easier to just actually find the values instead of finding z-scores first. But we can find z-scores. Right? The z-scores are going to be z1, which is the smaller one, is 1,000 minus 1152 divided by 84. That's equal to negative 1.81. Z2 is 1,100 minus 1152 divided by 84. That's equal to negative 0.619. So this time when I calculate, I'm calculating the probability that your z value is in between negative point, the smaller one, which is negative 1.81 less than or equal to z, which is less than or equal to negative 0.619. So when you type this one in, it'll be normal CDF. But this time your lower bound is just 1,000 z-score, which is negative 1.81. Your upper bound is 1,100 z-score, which is negative 0.619. And we get 0.233, which is about 23.3%. If you want to, without going through the z-score method, you can type in normal CDF. Your lower bound is 1,000. Your upper bound is 1,100. Your mean again is 1152. Your standard deviation is 84. Calculate that. You get about 23.3%. Now, the next question says, what weight puts us there in the highest 5%? So when we started this process, A, B, and C so far have all been about finding percents. This time they actually give us a percent. So literally what you're doing is you're going backwards. You know the percent. You want to know what z-score or what weight from that z-score gave you that. When we do that, we're going to look at this bottom part right here. Finding a z-score when given an area. So we're given the area, which is 5%. You're going to use a different formula called the inverse norm. Inverse meaning you're going backwards from it. Inverse norm, to get there, you go second. Bars again. You have inverse norm, which is number 3. Inverse norm syntax looks like this. Inverse norm needs you to give it an area, written as a decimal. And it also needs you to give it a mean and a standard deviation. If no mean or standard deviation, are given, it is assumed that this is a standard normal curve, meaning that the mean is 0 and standard deviation is 1, which means it will give you back a z-score as the answer. So let's go back to this. This one I wanted to be in the highest 5%. So highest 5% means it's somewhere. Here's your mean at 1152. The highest 5% is somewhere out here. Here's the highest 5%. The way this formula works, it only calculates the left-hand side of the curve. So this formula will only calculate back this way. So when you type in inverse norm this time, you want to find this actual area, the green area. When you look at this, if the red area is the highest 5%, how much area is back this way? Well, you should see that, and this is 5%, and the entire curve is 100. Back this way is 95%. So when you do this formula here, you're going to do inverse norm. They want an area. The area this time is the green area, which is 0.95. Standard deviation is, the mean is 1152. Standard deviation is 84. When you calculate this, inverse norm 0.95, 1152, standard deviation 84. This is equal to 1290.2. So any steer that weighs this amount or more is going to be in the top 5% of weights for all steers. And if you want to, you can actually go backwards and calculate it with a z-score. Instead of typing in this mean and standard deviation, you would just do second vars. Inverse norm, again, 0.95 if you're looking at the highest 5%. The z-score that corresponds to that is 1.645. So basically this z-score, this weight right here we just found to be 1290.2. So because this weight is 12.0902, the z-score that corresponds to it is going to be the same thing as 1.645. Remember, you have a formula that says z is equal to x minus mu divided by sigma. So in this formula, what we're going to do is plug in what we know. We know z is 1.645. That's equal to, we don't know the x, that's what we're looking for. So this is x minus the mu is 1152 divided by the sigma, which is 84. We're going to solve an equation for an unknown variable here. To solve, we're going to multiply both sides by 84 first. Get rid of the fraction down here. So that's 84. So multiply both sides by 84 to clear the fraction. So that's times 1.645. This is 138.18 is equal to x minus 1152. We'll add 1152 to both sides to get x by itself. Plus. And I get x is equal to 1290.2 again. So this is the math that the calculator did for you when you did it the first time. When you do inverse norm, it's a lot easier to go straight to here than to do all this work.